problem that has a beam. And the problem shows us, just like every other problem, it gives us what the external forces are. So here we have a 10 kip force and a 10 kip force. What's kip represent? What? 1,000 pounds. It's not really called a kilo pound because kilo is usually more used for metric. So 1,000 pounds. Okay. A half a ton. Then there's a connection here. What have you seen mostly as connections? What are the two most popular connections you see? A pin and a what?
Fixed.
Actually, have you seen fixed more than rollers?
Yeah, rollers.
Usually rollers. So there's usually a pin. I'll just write pin here. And roller on this side.
Oh, you can.
On the ends. Yeah, most common on the ends. And a pin has a reaction of what? Let's go around the room. Clara, we'll start with you. What does pin have a reaction?
Y, X.
Y
Z
and
if
X.
there's a Z.
It's only 2D. So it would just be a force in the X and a force in the Y.
Yes.
But what do you notice when you look at this? What do you notice your X component of the pin would be? 0. Why? Because there's no other X forces, right? So in the end, we're going to wind up having a reaction of the pin, and if I do a sum of the moments about here, I'm going to find out that it's 10 kips. And then on the other side is a roller, and a roller takes what, Lonnie? Just a Y. And in the end, if I did a sum of the moments in the over here, or I did a sum of the forces in the Y, I find out that this is 10 kips. So I'm presenting these beams showing you the forces that have already been calculated as reactions and supports. I mentioned that this is all graphical. If you look at this beam, how many sections would you like to divide it up into? 3. Does that seem reasonable? There's a load here, there's nothing here, there's a load here, nothing here, a load here, nothing here. So I sectioned it off in 3s, and that's why I drew these lines going down, fleshing. This part right here is representing our force. And another term for a force is a shear. If I supplied a very great force to this beam and it broke, what kind of failure would it be? Shear failure. Let me say that again. You have a horizontal beam. I'm applying a huge load to right here, right? And it would break right here, right? It would be sheared. Do you remember in material, those of you who took materials, shear is when the load is parallel to the surface where the failure occurs. If I load it in this direction and my failure occurs right here, it's a shear failure because they're parallel. And we are in these problems, we are trying to calculate the force, the vertical force that's inside here due to vertical forces that are being applied. So we're looking at shear. So rather than calling it a force diagram, we call it a shear diagram. So this section right here is the shear diagram. And V is the variable that's used for shear. This blue line stands for 0 shear. There's no shear on it. And if I draw it above, it's a positive, and below, it's a negative. Okay. So let's walk through the problem. We'll walk through the first one, and then we have 3 more to do. So at this point, shear diagrams always start and end at 0. So they have to start and end at 0 because these are the ends. But Sarah, at this point, what load is this beam experiencing? 10 kips. Going up. So we draw it up to 10 kips. So Rachel, what is this beam experiencing between the 2 ends? Is it experiencing any loading between the 2 ends? No. So it stays at 10 kips. Because within that 50-foot length there's nothing happening between the ends, so the shear does not increase. Janae, what's happening at this point right here?
It's,
10 kip load going which direction?
10,000
Down. So I draw it going down. So far so good? I'm following the direction of the load. Chris, what happens within the 10-foot length here? Nothing. So I draw it 0. Chelsea, what happens next at this point? Goes down 10. Nick, what happens in this 15-foot length?
It's just going straight across.
Goes straight across because nothing's happening. And Nick, what happens at the end?
Goes up.
Nicholas, sorry.
No,
And then it goes up 10 kips. And now we color this in. This is what's referred to as a shear diagram. So Jack, if somebody showed you this loading up here from the shear diagram, what would be the answer to this question? What is the maximum shear that this beam experiences? 10 kips. So what do you need to design it for? 10 kips, more than 10 kips, right? Let's say if there was a factor of safety of 3, what would you design it for? 30 kips. Okay, so the maximum shear it's experienced is 30 kips. Let's say the left side only went up to 5 kips. Let's say the left side only went up to 5 kips and the right side went down to 10 kips. Santiago, what's the maximum shear this experiences?
5 kips.
Okay, so you may think 5, right? Because the 5 is positive and the 10 is negative. But it doesn't matter whether it's going to shear like this or shear like this. So the maximum value is actually 10 kips. You still have to design it for 10 kips. And those of you who took surveying, you know whether you're off a foot under or a foot over, you're still off a foot. Doesn't matter what the sign is. It doesn't matter what the sign is. Everybody good?
Yeah.
Let's go to the next one. Nick.
With these drawings, is it always going to be from left to right?
Oh, you could draw,
'Cause we
yes, always left to the right.
Okay.
Yeah. So skip this one because it's exactly the same, but we're going to do it a different way in a little bit. And now we're going to the next one. Okay. Oh, something I forgot. Very, very important. Look. I guess what I could have done, I wrote the units on here. But you know when you have an Excel table, where do you write the units? On the top of the column or at every number? Top of the column. So let's do the same thing there. Here, do 10, and here's where I put the units. Kips.
I have a question.
Yeah.
This graph kind of reminds me of some like energy conservation and physics. If you had, I mean, I'm thinking maybe a little bit too abstract, but if you have a force that's up but an opposing one, I mean, it still had like 20 total kips applied to it, but in opposite directions. Does that mean that it experienced double the force, or are the opposing
Okay.
kind of preventing it from failure?
Okay, remember, what is it, the third law? For every reaction, there's an equal and opposite reaction. Is that the third law? Right? So we're dealing with that here. We have 10 kips on the left side. We have 10 negative on the right side because they balance off. In the end, they have to be 0. So it doesn't experience 20 kips. In this section, it's experiencing 10 kips. Jose, what's it experiencing here? What shear is it experiencing here?
No kips.
No, nothing. It is not experiencing any kips here, any shear. And then Sam, what's the shear it's experiencing here?
10.
10 again. So you never double it. It's only experiencing 10 here or 10 here. It's gone up, this is 10 kips. So where, Esau, where do you think the failure may occur? In the first section, third section, first, second, third, and or. If there was some break in here, where would you expect the break to occur?
First or third?
First or third, because that's where it's getting the most shear. Okay. And so let's say the beam breaks in the second section. Did it break in shear?
No.
No. Isn't that awesome to know that? I mean, failure analysis is really cool. You look at something that broke and you figure out why did it break. If it broke in the middle, it didn't break through the shear, because there's zero shear there. No, I don't know if that quite answered your question, but I
No,
really.
it did actually, because I was thinking, how would it affect if you have equal and opposite forces?
Okay.
How is it gonna fail?
And it's not, yeah, so let's,
And so I
let's-
didn't realize that, I thought it would fail in the second, because that, but it.
right, but it doesn't, right? But it could fail in the second spot for another reason.
Due to
But
that.
we'll see. Let's see another one later. Let's keep going with this. So again, this is, what's this diagram here called? Shear diagram. And shear is another word for force. And we have to put units. We already have the 0, the positive, and the negative. So what units? Oh, we're dealing with kips again. So Uriah, we're up to you. So all the diagrams have to start and end at 0. So what happens at the beginning?
Drops down to 1.5.
Drops down 1.25. Daniel, what happens then?
Flat.
Flat. Eugene, what happens now?
Goes up
How much?
3.75.
Right. So what does it go up to?
2.5.
2.5, right? David, what happens from here to here? What happens in this section?
It is flat.
Flat. I'd probably use the word horizontal. Horizontal line. Okay. Larson, you have the tough one. So, okay, well, actually, maybe it's gonna be DJ. Let's look at this. Larson, is there, everybody look up here? Notice when there's a concentrated load, there's a vertical change in our diagram. Is there a concentrated load here? No, so there's no vertical change. But there's a distributed load in this section. What do you think happens?
I think it's going to be at a slant
It's gonna go down as a slant. How come?
because it's over the distance it
Right,
changes.
it's a distributed load of 1 kip per foot. So every time I go over a foot, I'm going down a kip. Right? So what does it need to go down to, Larson?
You do 1 times 5, and it's negative 2.5.
2.5. And let's go to DJ and then come back. DJ, what happens here?
It goes back up
To what?
to 0.
To 0. So I'll color this in. Hang on, Eugene. So everybody's comfortable with the concentrated loads, right? It goes down, you go down. Goes up, you go up. You get to here and you have a distributed load. Really what we're doing is, do you remember when we did distributed loads? I mean, you did it with me virtually, right? And then you did it with Karen. But do you remember the force was equal to the integral of W dx? And then the moment is equal to force times a distance, which makes it Wx dx. So when you're calculating a force, it's really the integral of this, right? And what's the integral of something? The area, isn't it? So the force is the area of the distributed load, which we knew already. Well, let's look at the area up there. DJ, could you calculate the area of that distributed load?
Yeah, 1 times 5.
1 times 5 and it's
5.
5, which means Here, we had a load of 1.25 and we went down 1.25 because the force was going down. That distributed load is going down and it's going down a total of 5. But we can't draw it vertical because it's a concentrated load. It's gotta be linear. This kind of line. Eugene had his hand up first, then Sam, then Rachel.
Doesn't the 2.5 have to go lower? Or something?
Yeah, not to
It's not to
scale.
scale.
Oh, it's not to scale. If I had graph paper, it would be better.
Do you need to take into account the 2.5 kips on the far right?
At the end, yes. And what did this 2.5 communicate? DJ, tell me. What did this tell us?
That told us that we go back.
We gotta go back up. Because remember that these shear diagrams have to start and end at 0. So it was a total check. We went through this whole thing and we ended up here and then we're like, oh shoot. But then you look here and say, oh, 2.5, good. And then it checked. And I said the O instead of the I. Rachel.
So you can't replace it with an equivalent.
You cannot replace it with an equivalent concentrated load. Great question. We know that it feels the same way, right? But not in terms of shear, and we didn't do these yet. There are bending moment diagrams. It experiences something different. But for equivalent systems, it was fine. Sam, you went. Okay, it was Jabin, then.
Oh, two kind of questions, I guess.
Yeah.
So we already figured out the equilibrium equation to find all those things are in equilibrium.
Right, so remember that there is some pin here, and there's a roller here. Well, I don't even remember which one. I don't know if the roller was here or here, I don't know which one was external. But I did the part you already know how to do.
Like you're
You
saying,
You had to do the equilibrium equations. You had to do these equations to find the reactions at supports. I just didn't take our time in class to do that because you already know how to do
but
that.
that's has to come first, right?
That's correct, that has to come first.
And the second thing is the 5, the 1 pound per foot or 1 kip per foot
Yeah,
distributed over 5 feet, it gives you 5 kips total, right?
yeah,
And then it balances with, I'm seeing the area, those two triangles isn't the area of the 5. It doesn't seem like it. I know it's not the scale, but even if you, it seems still half of the area.
if I took the area of this, and this is a good question, everybody. The area of this, the area up here communicates this. This area is going to communicate the moment. So we calculated the area here and got 5. That was a load, right? The load. That means this represents the load. The change has to be 5. The area here is, if you calculate area here, isn't it going to be force times distance? Okay, so let's go up here. The area here is 1 kip per foot times the distance gives me a force. The area here gives me my force. This y direction is my force. I have to have 5. If I calculate the area here, I'm multiplying force times distance, which is a moment, and so the area here will tell me what to do in the moment diagram. So this area up here, Jabin, communicates the vertical change. The area is 5, I gotta have a 5 going down.
So you're just integrating into the last.
I'm integrating. I'm integrating this to get this, and then to get this, I'm gonna integrate this thing. Daniel,
If we had a triangular distributed load then, would it be
Right.
curved?
then it would be curved. Great! It would be a parabola, either down or up. And we'll-
Just wondering, because we can make that distributed load into a point load, right? Is that,
Yes, that's what Rachel asked. You could, but not on these type of problems, you can't.
okay.
Because that's all you're communicating is the equivalent force. If you take a distributed load and turn it, everybody listen to this. If you take a distributed load and convert it to a point load, you're looking at what it's going to experience in the whole realm of forces, but
Right.
you're not communicating what it's experiencing right here in the beam.
Right.
So we have to keep it as a distributed load.
So taking that distributed load sort of takes away the internal forces, or,
It doesn't communicate
Doesn't
correctly
communicate.
the internal forces that are going on.
cool.
Good? Isn't this fun?
Yeah.
Hardly any math.
Yeah.
I mean, I love math, but I really like graphs. You can color it in, you can have crayons. Only get Crayola though, those crappy ones they give you in the restaurants. They're not even worth melting.
Randy, bring your own crayons.
Okay, what do I need to put here?
Shear that.
Units. Okay, Kyle, we're up to you. What happens first?
Goes up to 1800.
Well, I rotated them. Just find this picture. I shouldn't, say it again?
It goes up to 1800.
Goes to up to 1800. It originally was the second problem, but then I decided it should be the third. Okay, Geraldine, what happens here?
It's going straight across.
Straight across, nothing. It's not experiencing any load here. Maria, what happens next?
It goes down 1,500,
Goes down 15, so it goes down to what?
300.
300. Then Lucas, what happens here? Horizontal. We're still at 300. Eric, what happens next?
Then it's a diagonal line that's going down,
Right?
and it's gonna be 2,500.
Right, so the area here is 250 times 10, which equals 2,500, but we started at 300, so what does it go down to?
2,200.
2,200. And then Enrique,
And it goes up by 2,200, which is to 0.
which is to 0, which makes us happy, right? Good? So Sam, what is the maximum shear this beam experiences? 2,200. It's the maximum absolute value. It experiences 2,200 shear. Where?
The far right.
All the way at the far right. Where does it experience 0 shear? That point, right? Which would be nice for us to be able to figure out. We could do it by a slope diagram. And it turns out to be, I think, 1.2. Let me look it up. Oh, it's in this packet. Is it 1.2? One point two. And how do you figure that out? Y is equal to mx plus b, you know what the slope is, you know what the y-intercept is, you find out the equation. Okay, good, let's do one more. So notice, this concentrated moment has nothing to do with the shear. Has nothing to do with the shear, but what does it have something to do with? The moment diagram later.
What if you were to have forces going along X?
Horizontal?
Yeah, would
It's
we?
because we're dealing with beams, so beams are only going vertical.
Okay.
You only do this with beams. I mean, I guess if it was a vertical member, you know, and we had all the forces like wind and soil and stuff, you might analyze it for that too.
But you'd never
But
have.
typically you're doing it on a horizontal thing.
So if you had a force going like, had an angle to it where it's not completely vertical, but it does have a Y component, then you'd find
Then
that
you'd
by.
have to use the Y component.
Okay.
You're not gonna see problems like that.
Okay.
Okay, this is the next one. So, and you always wanna draw these lines down. So this one, how many of you wanna, Aaron, how many, I mean, I already sectioned it off, but how many sections does it look like it should have? Does 4 seem reasonable?
1, 2, 3, yeah.
Yeah. Because something different happens here. See this concentrated force? There's a concentrated force and a concentrated force. So it looks like, everybody look up here, it looks like this would be an important spot that changes, change. What do I need to put here, Aaron?
You need to put the units, yes.
Okay, Aaron, you wanna do the first?
Page 4.
So we start at 0, then what happens,
Then we have a distributed load,
right?
18 times 9, it looks like? Or is that, no, that's a moment, huh?
Right.
Okay, so 18 times 1, so 18 kilonewtons.
What's the distance?
6.
Well, we're doing the first section, right, we're dividing it up because there's a concentrated force here of 112. So it's 18 times 2, Aaron, no? I don't hear you saying 2.
But I don't see where you're getting this to.
Here, look, the distance.
Yeah,
You
the
see it?
The distance to the 112.5 kilonewton force?
Yeah, this first section right here, I'm looking only at this section of distributed load, it would be 18 times 2. So what's the shape of my shear diagram?
I don't see how that's 18 times 2.
If the distributed
Well, the
load-
18
Is it
kilonewtons per meter, right, you
18
see
high?
that?
Is it 18 high?
Yeah,
Okay,
yeah.
I'm thinking of something here, right?
No, it's distributed loads, it's applying 18 kilonewtons per meter, so the total here would be 18 times 6.
Right, okay, so the
But
total
we're
for that
only
area
looking
is
at this 2, so it's 36.
36, yeah.
Now, how do I draw this? Aaron,
Down to 36 as a diagram.
a diagonal line to 36. Thank you. You guys, look up here. I wrote kilonewton meter. I don't know what I was doing. Okay, Jabin, what's next?
I would think it keeps going maybe, but then there's that arrow that goes up,
Right, and that arrow is an external load that's going up.
jumps up
We gotta jump up.
to 100.
It has to jump up 112.5, right? So what does it jump up to? Because it's coming from 36.
Work that out.
76.5. Nicholas?
Does the 18 not decrease that at all at that point?
Not at that point,
Okay.
no.
Wait, isn't it just 36 minus 1,125?
It's 1.
112.5.
Why does the 18 not decrease it?
Because it's gonna decrease it now, and we're up to you, so this is perfect. So now, Claire, what happens here?
It's going to go down.
Right.
4 times 18.
Right, which is 18 and 18 is 36, 36, 2, 72. So it's gonna go down 72, which means this is gonna be
4.5.
4.5.
So.
Okay. So everyone look up here. Take a guess at where these connections are. Where are the supports? Right here? Right? There's a support right here. One's a pin, one's a roller. You calculated these two forces. Those are the reactions at the supports. So these did take into account the 18, because this thing is in static equilibrium now. When you draw the shear diagram, you have to go step by step. So here, it was 0. Then in this section, it went down because it's a distributed load. When you hit this point, there was a reaction at the support, so it goes up 112.5. Then this goes down. Good?
Yep.
Okay, Lonnie, what happens here? Straight across. Keep going, since you got an easy one. What's next?
Okay, then it's gonna go down 36, 36,
Right, so it goes down to what?
30.
31.5. Sarah, what happens now?
Goes up to straight, goes horizontal, then back up to the
Right, and then back up, and then color it in. Rachel, what is the maximum shear? Right, and where is it experiencing it?
At 2 meters from the left side.
Left end,
The-
good. All right, are we good?
So
Sarah?
experiences the max shear where the, I'm trying to,
Yeah,
I'm trying to
yeah.
put the
So,
analytical into.
yeah, you
a
can't say the maximum shear is at a certain point. You cannot say maximum shear is at a support. Maximum shear is where the distributed load is. Maximum shear, you can't make an overall statement. You have to draw it first. Because the shear diagram is a function of all the different forces that are on the system. So it's not until you draw the whole shear diagram that you can see where the maximum shear is.
So I get where the maximum shear is, but it's 2 meters from, okay. Cause in the last one, we showed like the point where it's experiencing that shear.
This is a zero shear. It is not experiencing
Oh,
shear
okay,
here.
so I got there, okay.
Yeah, so what's the maximum shear here?
22.
2200 right here. This is where it's experiencing no shear. If it fails there, you know it didn't fail in shear.
Oh, okay, that,
If it fails here, it doesn't experience, you know it didn't fail in shear. Oh, no, that's not true.
it's only if there's a horizontal.
Right. If there's, here you know it's zero, but here it experiences 4, yeah. Okay. Good point.
You gotcha.
Okay, let's go back to the first one we did. Larson, you look like you had a question. What I was just talking about now?
Yeah, it did. It was.
Let me just repeat this. That here, the only shear present is zero. It's not experiencing shear at all.
Okay, so my question
But
was.
here, when it crosses the x-axis, it actually has a maximum shear of 31.5.
Okay. So my question was, is it only gonna like break through like a shear force?
No.
Only at the maximum?
No, because let's say, let's go on and do the moment, because it might fail in moment, right? So a shear we know is when a load is applied. A load is applied right here, and the shear fails right here, parallel to the load. What's a moment failure? If I take this and I bend it, and it's experiencing a big moment, it's gonna just pop and break, right? So it'll bend first, hopefully, because we're gonna use ductile material. But if it's bending due to moments rather than bending through to shear. So, sorry, I didn't say that right. Is it failing, look, is it failing due to shear? Look over here, is it failing due to shear, or is it failing because I put a moment on it? Okay. So let's do this. So let's go back to here. What is the moment? How is the moment related to the force? The moment is the force times the distance, right? It's the integral of the force diagram. The moment is equal to the integral of the force diagram, which means the moment is equal to the area of the force diagram. Hang on. The shear diagram is equal to the area of any distributed load. The moment is equal to the area of the force. Okay, Rachel, you have your hand up?
So the axis where failure occurs, if it fails to the moment, would be perpendicular to the moment?
No, there's no direction on that because it's kind of similar in that the shear, it's always going to be failing perpendicular to the beam.
Right, if you have a moment, then like it would be like coming out with
The moment is definitely in the z-axis, right? It's a spin in the z-axis, but it's causing failure along this line. Let's do some numbers, and then we can get more of a better feel of it. Okay, so moment diagram. First thing we have to do, make sure positive, negative, put a 0 in, and you have to put units. What are the units? Right, hip, foot. Wait, foot pound, foot hip. We put the foot, the distance first. Janae, I think I'm up to you. So let's look at this diagram. Everybody, we're going to go through all these diagrams. Is this a positive area or a negative area? This one?
Negative.
Next one? What's this?
Negative.
Negative?
Positive. Positive, negative.
What's this one?
Positive.
Positive, 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 negative. Negative, positive, positive, negative. So how do you think that positive or negative area is going to tell us information about the diagram? When I think it's the slope. So Janae, all these diagrams, even the moment diagrams, they always start and end at 0. Another way for us to check ourselves in statics. So Janae, what do you think we need to do?
probably gonna be positive slope.
Yep. And what's it going up to?
10. Quick course?
You gotta find the area. What's the area?
Well,
10 times 15, 150. Because the height of it is 10, and the width of this, to calculate the area, is 15. It's gotta be, what? We're gonna have a slope of 10. Okay, Chelsea, what's happening in the shear diagram? So you guys, in order to find out what was going on in the shear diagram, we looked at the force diagram. Now, in order to find out what's going on in the moment diagram, we only need to look at the shear. What is happening here? Nothing. So what did we do before when there was nothing? Horizontal line. Nick, what happens here?
You have the same slope as the upslanted one, but it's going down now.
Okay, so calculate it for me.
It's
10.
150 again.
10 times the 15, so it's going down 150. And does it close? Yes, and is that a good thing? Yes, it's a must. So Nicholas, what maximum moment does it experience?
150.
Say it again?
150.
150. So notice, the middle section for shear was what? 0. But in moment it was 150. If it fails in the middle, what do you think it probably failed in? Moment. Because it's experiencing a moment, it's not experiencing a shear load. Isn't this neat?
Would you say it failed to the moment?
Sam, I don't know why I'm intrigued about failure, but
So is the failure of the moment 15 times greater than the failure that would happen at shear force?
you can't do
You
that.
can't compare
No.
that? Okay.
You could just say that it's experiencing a maximum shear in that second section, and it's experiencing no, a maximum moment in section 2, but it's experiencing no shear in section 2.
With these diagrams, could we tell where this member would fail at?
Yes, but it really, in addition to failing in shear and moment, so this is the moment diagram. It's typically called the bending moment diagram. But you could have just say moment diagram. It's not just shear and moments that create failures though, right? And those of you who took materials, corrosion. If there was corrosion in a certain place, it could fail in that place and have nothing to do with shear or moment. There could be, materials are supposed to be homogeneous, but they're not. We can't make perfect materials, they're heterogeneous. If there's a weak spot, it might fail there due to a weak spot, right? If something's been, those of you in materials, those places that have been cold worked, right? It's built up a lot of stress in there. If it's been cold worked, that area already has a lot of high stress and it might fail. So there are other reasons. But for these two reasons, yeah, if it failed in the first or third section, it was probably failing in shear between these two. But we could definitely say that if it failed in the second, due to one of these two, it would have been moment.
So that's the only thing we could tell with these diagrams
This
is
is the
that,
moment in the shear that it's experiencing.
and whether it's, okay.
Jabin?
So positive and minuses, is it truly the moment or the
slope.
sense of the moment, or is it the slope?
So I'm going to tell you the whole idea about the standard direction, at some point. But right now, if you have a positive area, you know it's a positive slope. Negative area means negative slope.
And that refers to actual like right-hand rule sort of stuff, or?
It's really the sign convention that's determined for this. I could have drawn it, this is an aside, I could have drawn the whole thing. This here, this here, this here, this here.
I'm noticing
Depends on our
it might matter because it has moments on some of these other ones.
Yeah, and we're gonna get to those. Right. So, hang on. So right now, are you comfortable when the force goes up, you go up, force goes down, you go down? If it's a next problem where we have a distributed load going down, the diagonal goes down. Everybody's comfortable with that. Okay, now, you have a positive area in the force, it's a positive slope. Negative area, negative slope. Everybody's good with that? Okay. So I'm moving you from, in step by step, so make sure that you're getting what I'm doing and ask questions on that. Then let's move to the next step and then I'll explain it and then you can ask questions. So Lonnie, do you have a question on what we already did? No. Okay. Sam?
Maybe, so since the area seems to be positive in the moment diagram,
Yeah.
does that mean it's a positive moment?
So if it's, no.
No?
No, it's based on the sign convention. That's Jabin's question too, so let's wait a little bit. Okay, so let's look at this one. Where are we, Chris? No, we went further. Oh, but you were missing, so you're next. Well, were you here for any transfer from the shear to the moment? No, right?
I think I got it though.
Okay. So it always starts at 0, ends at 0. What's my units here?
Foot per kip?
Foot kip, not per kip, foot kip.
Okay.
Okay, so what happens in the first section?
I don't know the distance.
Okay.
That would be helpful, but.
Right here,
Okay. Oh, I can look at my sheet. What does it say? 16?
10.
10? 10 times 1.25, which is 100.
12.5.
12.5.
And what do I do?
You're gonna have a slope going down.
Right. And I'm going to go to
12.5.
12.5. Chelsea, what's next?
2.5 times 5, which is
2.5 times 5, which is
12.5, so you go back down to 0.
up to 0, right?
Or up to 0, sorry.
Right. Nick? Oh, no, sorry. You got a second. Jack, it's your, well, whose turn is it? Nicholas's? Jack?
Maybe like a parabola kind of shape.
A parabola, so now let's think, so now I have my little cheat sheet that I'm sharing with you. But you don't really need a cheat sheet because you have parabolas swimming around your head and integration swimming around your head. But mine, it was swimming around my head a long time ago. So I made up cheat sheets for myself. So when going from a shear diagram to a bending moment diagram, if I have a positive area, I have a positive slope. Negative area, negative slope. Negative slope in a positive area is parabolic going up. Negative slope, negative area, parabolic going down. If I have a second order, a parabola, I'm getting a third order. You know that already without me showing you this, but this is helpful for me. If you did all the integration.
Joanne, going back to the problem.
Okay, let me just remember these two. So negative slope, positive area goes up. Negative slope, negative area goes down. So let's just finish this. So negative slope, positive area goes, Jack? Up. And then the negative slope, negative area goes?
Down.
And what's the high point? What would the high point be, Jack? How do you calculate that? And how'd you figure it out? You gotta do area, right? The area of the shear diagram is this. The moment is equal to the integration of the force. So that moment is equal to the area in the shear. What's the area here? 1/2, 2.5 base times height. What's that come out to be? 2.5, right? No.
No.
2.5 times 2.5 is,
6.25.
is this 3.125? Should I write it? I'm writing it with a pen.
No.
3.125.
3.125.
And then it curves down,
6.5.
and then we color it in.
6.25.
I really want to finish the last two problems so you're comfortable. What's the maximum shear? 12.5 where? 10 feet from the left. Okay, Santiago, we're up to you. Okay, I have a couple of questions first. So Santiago, in this first problem, were there any concentrated moments? Everybody needs to listen. In this first, just look up here. In this first problem, were there any concentrated moments? No, they were all concentrated forces. In the second problem, were there any concentrated moments?
No.
Concentrated moments, like a screwdriver in spinning it? No.
Right.
But in this third problem, we're introducing something new. Is there a concentrated moment? Yes. So what I do is I always put a dot down here. So I remember I have to go back up. Because where do we get the information for the moment diagram? The shear diagram. Again, where do we get the information for the moment diagram? From the shear diagram. Except, if there's a concentrated moment up here that I have not communicated here, I have to remember to put it here. Okay, so I put a little mark. So, first thing, units, right? What is this? Foot pound. Start at 0, end at 0. So Santiago, what happens first?
Was that square, the area is 9,000 going up?
Right, so 1,800 times 5 is 9,000. Now, Jason, you have the hard one.
Nice reaction.
Okay, so look up here. So you looked at the area here and you went up because it was a positive area. At this point, I have a little dot, a little mark that's saying there's a concentrated moment. What is this moment? Positive or negative? Positive. You have to draw it negative. You have to draw it the opposite. And I'm not going to explain why today. I'll explain why another time. Just remember, if the moment's positive, how do you draw it? If the moment's negative, how do you draw it?
Positive.
If the moment's negative, how do you draw it?
Positive.
If the moment's positive, how do you draw it?
Negative.
Okay, Jason, what do I do with this 1,000? I go down. So that's the answer to Sam. Well, you don't have the answer yet. But Sam, you asked why. Jabin, you asked why. And we'll talk about why, but not today. Because I want to do the problem. Okay, what happens next? Jose? I went went down 1,000 and now I don't have to look back up to the force. What's going on here? Positive area, right?
Yes, so you're gonna go up at a diagonal, 300,
300 times
5, which is 1,500.
1,500, and I'm going up from 8,000, so it's
20?
9,500. You said 15 up, right?
Yes, I just can't do that right now.
Sam,
Yeah.
the next part, we have a triangle, has a negative slope, positive area. Which way does it go? Up. So let's carry this guy down. And what does it go up to? What's this area here? The area is equal to 1/2 the base, which is 1.2, times the height, which is 300. 300, that's 1.5 times 2, 1.2. Somebody do the math. Like 16 or something.
Joanne, did you forget the 1,500 pounds in the second?
It's 180.
Yep.
180. Hang on a second. What, Eric?
I'm sorry,
Found
no,
it?
no.
Okay, so it goes up 180, so Jose, oh no, I'm in Sam. Sam, what does it go up to? What number?
9,680.
Right. And then let's figure out this area here. So Isak area is equal to 1/2, what's the base? 8.2, no, 8.8, right? Times the height, which is 2,200. So what's that? 1,100 times 8.8.
9,680.
How do you know that without doing the math? That it should close, right? But you want to check the math to make sure. What's the maximum shear, Isak?
Maximum 9,680.
Up, 9,680.
Wait, you
That's
got.
not-
Sorry, maximum moment, sorry. I meant moment. He knew what, he was reading my mind.
Yeah.
Rachel?
So, like, you know how that concentrated moment, it was going this way.
We're gonna talk about whether it's positive or negative another time.
Use the left hand rule.
No, no. It's all to do with the sign convention and you have to wait. Okay, let's go to the last one. So, Daniel, a quick look up to the top. Are there any concentrated moments? Yeah, where?
Concentrated?
Yes.
At 2, that.
It's, look at
Oh,
your
concentrated
sheet.
moment, sorry, yeah, 0.
It's at 0, so put a little X mark here, right?
Yeah.
Okay. So it happens, so you always have to look up there to see if there's a concentrated moment. So, Daniel, it's a positive 9, so what do you draw?
Negative.
Negative 9, go down to 9.